Welcome to Young Tuition. This is part of in-depth lectures on climate change studies. Today, I'm going to introduce some of what I have done in the past few years on climate change. Well, my original research background was in electron spin resonance spectroscopy, namely the resonant absorption of microwave by spins of electrons and nuclei in the presence of magnetic field. So microwave and infrared wave are not far away. Okay, if you know the electron magnetic wave spectra, you know that the infrared is here and far infrared is here and microwave is just next door. Well, the infrared absorption is the key issues in dealing with climate change. Today, I'm going to answer you the most popular question, namely whether or not CO2 and other gases in the atmosphere can make the surface temperature increase. To help you to understand my talk, I prepared this Desmos file in which you can see some of the basic formula I use governing the variable to be discussed. In this small window, I also trying to show you the vertical distribution of this variable. So the x-axis represent the altitude in unit 10 kilometers. For example, 2 here means 200 kilometers. And this y-axis will represent the intensity of radiation in the unit of watt per meter square. First, I just show you, indicate that this vertical dash line will represent the infrared radiation intensity by the surface, based on the surface temperature, which is everyone assumes that at the moment, the global mean surface temperature is about 289 Kelvin. Is the dash line corresponding the budget of the infrared radiation of the surface atmosphere system. And the first variable I'm going to use is this, the green curve. Can you see the green curve? It represents the transmitted energy at a different altitude. So that actually is called transmission, just simply called transmission. So that represents the transmission, represent the percentages of the infrared radiation of the surface still remain by the time if you measure the transmission at a different altitude. Can you see that? Obviously, the closer to the surface, the transmission is almost the same as the surface temperature. But because the air density is the highest near the surface, so therefore, due to the absorption, I'm going to introduce absorption, and the transmission will decrease faster. But eventually, as air density decrease and the transmission eventually became asymptotical value is limited constant. The second variable is very important. That is uses a purple colored curve. It is called the atmospherical absorption of infrared radiation from the surface in this case. And as you can see, similar, it is a reciprocal. You see, basically almost reciprocal. And I'm talking about this exact relation later on. But from this graph, you can see as the absorption increase and the transmission decrease, it's quite logical. It's quite logical. Of course, this study is not to repeat this simple phenomena. Rather, it is focused on, it's aimed at to derive the quantitative description of the equilibrium state of the surface atmosphere system. Now, another important variable is called the emission, atmospherical emission of infrared radiation. So like any hot object, under certain condition, atmosphere will emit certain amount of the thermal energy to the cold places. In this case, and I must emphasize, unlike other researches, the atmospherical radiation refers to the net upward atmospherical infrared radiation into the outer space, because for the simple reason the outer space is much colder than the surface. And so bear in mind that when I talk about atmospherical radiation, I mean the upward radiation, not the downward. Okay, I will talk about that. The downward radiation is another issue, which is people use to make their argument in order to invoke the so-called the greenhouse effect. Okay. Another diagram, another graph is, oh yes, this one. Can you see this origin, the golden color? So these curves represent what we call the outgoing infrared radiation, or some people just call the outgoing long wave radiation, or OLR, if you can find this variable very frequently in the published papers on climate change. Okay, I will just confine to these four variables, and the independent variable I'm going to use is what we call, this is A here. The independent variable is called the absorptibility of atmosphere absorption in the infrared region. So we can see that if can we just reduce this A to 0.4, okay, that is the minimum value according to my calculation. In other words, if the absorptivity is less than 0.4 or 40%, our atmosphere will not emit any energy, okay? And in this case, you can only see two curves. So one is because in this case, the transmission is just equal to the outgoing long wave radiation. But if I just increase that percentage of the absorptivity, that means that if we just added more water vapor or CO2 and other so-called greenhouse gases, then you can see that absorption will increase, while can we just switch off the emission first? So you can see that as the atmospherical absorption increase, the atmospherical transmission decrease. That's logical, right? Because that is what people described as the blocking. So when you added CO2, and because in that atmospherical window, and the CO2 is over, the absorption frequency is very close to the upper edge of that atmospherical window, so that they can block. Indeed, if you just purely consider the absorption, they can absorb certain amount of the surface radiation into the outer space. Okay, of course, that is a starting point for the greenhouse effect, because people think that, well, because of the blocking, and that radiation were trapped by this greenhouse in the atmosphere, and in addition, there will be subsequently they will radiate most of the more than 60% of the absorbed energy will be downward, so that the underneath air will getting hotter. So ultimately, the surface temperature will increase. So that is a logic, that is a hypothesis in the greenhouse hypothesis. But unlike other studies, it is found that as the atmospheric absorption increase, above the 0.4 or above the 40%, and then the atmospheric absorption upward. This is a net upward infrared radiation by the atmosphere will increase. This is when the A reach to unit or 100%, So ultimately, before the air density became zero, the atmosphere can, under this condition, can absorb 100% of the surface infrared radiation. Can you see that that is the purple color reach to that the horizontal dash line. The horizontal dash line is the budget, the infrared radiation budget of the Earth's atmosphere system. Okay, but what I found something new is that the sum of the atmospheric emission, upward emission, and the transmission, the sum of these two, because these are all upward radiation. Okay, one is come originally from surface, another is come emitted by atmosphere. The sum of them is always constant. Look, if I just keep that parameter change continuously, you can see that the golden color curve remain constant. Remember what does it represent? Can you just switch off and switch on? So this curve represent the upward infrared radiation. Eventually you can see that the amount is equal to the surface radiation at the surface. But as the altitude increases, and eventually when the density of air density of atmosphere diminish, become zero, almost zero, and that amount of radiation become constant. And this constant can be treated as invariant. And that is determined by the solar constant or solar radiation intensity and the albedo, or the effective reflection of the Earth of the surface Earth atmosphere system. In essence, the outgoing long-wave radiation is independent of the atmospheric absorption of the infrared radiation. In other words, no matter how much water vapor, or people probably more concerned about the CO2, no matter how many greenhouse you added in the atmosphere, and the outgoing long-wave radiation will remain the constant. So that is an important result or outcome of my recent research, that the outgoing infrared radiation were not affected by the amount of the greenhouse gases in the atmosphere. Well, this is all of this I can show you is based on my recent publication in this journal. If you Google that, that's called the Progress in Physics. Okay, if you go to the website, and you will see this is open access, so you can download it anytime. So if you just go to their recent publication, so this is my paper, the third one, a quantitative description of atmospheric absorption and radiation at equilibrium surface temperature. An analytical theory is abstract. The analytical theory is proposed for the Earth's atmosphere system at its equilibrium surface temperature, 289.16 Kelvin. A nonlinear relation is formulated between atmospheric absorption and atmospheric radiation by modifying Kirchhoff's law on thermal radiation. For the first time, the global energy balance can be realized in a wide range of atmospheric absorptivity, transmittance, and surface emissivity. It is revealed that atmospheric radiation becomes negative once the atmospheric absorptivity is below its threshold value, that is 0.4 or 40% I mentioned. It is proven that the upward cumulative long-wave atmospheric radiation spontaneously increase. So from the 3.8, almost nothing, very low, to 199 watt per meter square as the long-wave atmospheric absorptivity increase from 0.4 to 1 or 100%. Whereas the long-wave atmospheric transmittance decrease from 0.6 down to 0.1 at constant temperature. Okay. I think today I'm not going to detail, but just outline some of the key results in this relevant to the diagram I'm showing you. So one is figure, if you draw attention to this figure called figure 2. So the vertical, the y-axis represent the atmospherical transmittance, and the x-axis represent the long-wave atmospherical absorptivity. And traditionally, and even up to now, it has been taken for granted that the relation between these two variables is linear. Can you see that is a dashed straight line? However, as I have discovered in my recent study, the more realistic dependence must be quadratic, as illustrated by this parabola curve, solid line, you see. And the related equation is just on the left. Can we just enlarge the part a little? The related equation is just illustrated in this equation, in the equation 21. So this tau represents the transmittance, and the A represent, as I told you, is absorptivity of the atmosphere, atmospherical absorption of infrared radiation. So you can see, obviously, this is a quadratic. It's not a straight line. Okay, so that is like the key result. I think also I would like to show you. So this is a this is table. In this table, you can see that I have to calculate based on this is input parameter. So this is experimentally observed value everyone use. So that's for including the global mean surface temperature, the albedo, nearly 0.3, solar constant, reflected solar radiation, and the shortwave atmospheric absorption, and the surface solar shortwave radiation. So that is how much solar energy can actually arrive the surface of Earth after it goes through the atmosphere downward. So that is experimental data, experimental condition, observation, experimental evidence. And here is this table is just some of these calculation, but you can see that my calculation is in a wide range compared with other previous authors. For example, in these two reference, this group, research group, only calculated the particular variable under one condition. In this case, they only assume that transmittance is close to 10%. That's it. But in my research, that the range, I announce these transmittance and other variable, other thermodynamic variables. You can see that the range, when I used the range for transmittance I used is between 0.1 and 0.6. Okay. So this obviously is quite different from previous studies, which only focus on particular fixed numbers when they're talking about the boundary condition of climate modeling. You see, the boundary conditions are essential to understand the climate system, which must be satisfied. Okay, but previously, because people mixed up with climate change, with the weather change, so therefore they have never reached the proper, the balance, energy balance at the surface. So therefore, this is the first time that the radiation balance, not just radiation just part of the three thermal transfer or heat transfer mechanism, that is including the thermal conduction, thermal convection, and the third one would be, and also you have to consider the mass transfer. It involves the phase change. So that is a full mechanism. So radiation is just part of that, one of them. The four mechanisms must compete among themselves to emit or to transfer the energy. So you cannot assume that there is always one mechanism there. Another important result I have just to support my illustration is this diagram, the last diagram, figure 4. You can see that these the horizontal, the x-axis represent again the non-wave atmospherical absorptivity, and the vertical one in this case is the total atmospherical radiation. So that radiation includes all directions. Radiation actually can go all directions in principle, including downward. But of course, in my study, the curve I used is just the net upward one, not the downward one. But if you consider the dependence of the overall, the total atmospherical radiation, then you will find that the dependence is simple, it's linear. But very interesting thing is that you can see when the absorptivity reached to the 0.4, or it's lower than 0.4, the atmospherical absorption becomes negative. So what does it mean? Negative. Negative is that they don't have, not only they cannot remit the energy outside, but they have also help the atmosphere to gain the enough internal energy. Otherwise, it's just too cold, which is forbidden by the basic law of thermodynamics. So that's why when working close to the hot material, you will get hot. Okay. But the most important thing of this diagram, what this diagram tells us, the atmospheric emission, it depends linearly on the atmospherical absorption. Simple. The greater the atmospheric absorption, the higher the atmospherical radiation. Okay, and to end this talk, I would like to play some music for you. Can you hear that? This music is played by my daughter. In summary, our atmosphere knows how to adjust itself in the presence of both solar and surface radiation. And by nature, and nobody can control this adaptation process. Okay. It is natural. If you know that there is a law called the Chatelier principle in thermodynamics as well as in chemistry, it states that any system, such as atmosphere, will oppose any internal change caused by external factors, so that they will create something to slow down or oppose this change. In our case, due to increase of the atmospherical absorption, the atmosphere spontaneously increase its emission, so that the sum of upward atmospherical infrared radiation and the transmission would be kept the constant, as shown in this golden color. So take it easy. The gas, whatever the gas is in outer atmosphere, cannot change the thermal equilibrium determined by the solar radiation and the surface as a physical property of the Earth. Okay, relax. And just keeping watching these channels, I will explain more fundamental issues associated with this discovery. Thank you for watching this channel, and have a nice day, and goodbye.